Okay, hi everyone. This is lesson 3, experimental probability. So we're going to read through our definitions to start. One of the major branches of modern mathematics is the mathematics of chance, commonly called probability. Probability is a number that gives a measure of how likely an event is to occur. Probability theory deals with chance, random variables, and the likelihood of outcomes. So an experiment is a sequence of trials in which a physical occurrence is observed. If, for example, toss a coin 10 times and observe how many heads you get. A trial is one repetition of an experiment or one toss of the coin. An outcome is the result of the experiment. So we can have a set of outcomes. H would be the heads, T would be tails. So heads, tails, tails, heads, 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 tails, heads, tails, heads, a random set of 10. The sample space is the set of all possible outcomes. It's sometimes referred to as the universal set, so that's heads or tails when you're flipping a coin. The event space is the collection of a group of outcomes of set of the sample space, a subset of the sample space. So capital letters excluding S are used to represent an event set, and it contains the specific outcomes of the experiment you're interested in. So it's still H or T, heads or tails. If you're trying to find the probability of rolling an even number with a die, then the sample space would have the 6 different faces with the 6 different numbers on them, 1, 2, 3, 4, 5, 6. And the event space for rolling an even number would be 2, 4, 6. A simple event is an event that contains only one outcome. So if we're saying what's the probability of rolling a 2, there's only one way or one face that has that 2 on it. So it'd be simple. A compound event is versus an event that consists of more than one possible outcome. So rolling a 2 on the first roll and then an even number on the second roll. The probability of an event is a number between 0 and 1, 0 being impossible and 1 being certain. And for any event A, the probability of event A is the probability of an event A so that it's between or less than 1, less than or equal to 1, and greater than or equal to 0. A fair game is a game in which all players have equal chance of winning. A simulation is an experiment that models an actual event and the law of large numbers. This is what we'll see today. The more times an experiment is repeated, the closer the outcome should be to theoretical probability. So our first formula for probability is the experimental probability formula. And the probability of an event A occurring is the number of times an event A has occurred out of the number of trials. So we're going to do an experiment here, using results from my previous class. We've got toss a coin and record the outcome. Repeat the process 50 times. Find and list the experimental probability of tossing a head after 10, 20, 30, 40, and 50 trials. So my first outcome, my first set of outcomes is going to be just that. There should be 1, 2, 3, 4, 5, 1, 3, yeah. There's 10 outcomes there. And if we're interested in tossing a head, then I've got to count up how many heads presented themselves. So 1, 2, 3, 4. So the experimental probability for that first set of tossing a head would be 4 out of the 10 trials. I'm going to do this again for another set of 10. In this case, this next set, I've got 7 heads. Kind of unlikely, but it happens. And so I'm just going to group these first 2 together and say, well, if I treated this like a one big set of 20 trials, how many of them would be heads? Well, that would be 11 out of 20. Just talking about on the side, theoretically, we should already have been exposed to the fact that getting or tossing a head, the likelihood of that is 1 out of 2 because there's 2 sides of the coin and only one side has the head on it. So when we look at the 10 trials and then the second set of 10 trials, those likelihoods are not 5 out of 10 individually. But when we group them together and increase our trial size, it's getting closer to the theoretical probability. So this one would then, if we grouped all 3 sets together, we'd be at 18 out of 30. Theoretically, out of 30, it should be 15. But we're still kind of bouncing around the theoretical probability. And as we increase our sets here, we should see it getting closer and closer. This one would generate out of 40 when we group it together. Maybe out of 24. This one was just 2 out of 10. But then we'd be at a total of, out of 50, we'd be at 26 out of 50, which is the closest we've come to match that theoretical probability. Okay, so 26 out of 50 is 52%. Whereas when we started, this one was 55% versus 60%. And what I'm doing here to get these percentages is just dividing them numerator by denominator and multiplying by 100. And this was 60%. So the law of large numbers states that the more trials, the closer our probability should become the theoretical probability. So in the middle there, we were getting further apart, but that happens. But by the end, we were getting closer to the theoretical probability. And the last experiment here, I'm going to use a simulation for using Excel. So I'm just going to quickly open that up. The random number generator, just so that you can see that occur. We're going to go, I'll just move down to the cell. It's the random between formula. See how it kind of generated there, enter. But I'm going to put in, I want random between. And I want them to be between 1 and 6. How come that's not working? Formulas, insert function. Okay, yeah, 1 and 6. Okay. No, it's still not taking. I think I've messed up this little part of the board. Oops. Insert function. Oh, here, this is the other one. Oh, yeah, it is the whole word. Bottom, top. Yes, because I have it twice. Still not working. Rand between. Let's try 1 to 6. Okay, yeah. So that's the formula. I don't know why it took me so long to put it in there, but it's the rand between formula, and I want it to start at 1 and end at 6 because the dice have 6 sides, right, with the numbers 1, 2, 3, 4, 5, 6 on them. And if I just autofill the rest here, so I'm going to take my cursor and just put it on that little green box in the corner. I'm going to drag down, and I want 10 random numbers there. So 4, 2, 4, 6, 5, 3, 1, 3, 5, 4. And I can take this formula and then just copy it and paste it. Nope. So this would be my second set of random numbers. This would be my third set. And every time I'm doing this, all the numbers are just generating again. That's fine. I'll just take my last set here as my final, because it was 50 times as well. So the experiment 2 said roll a single die and record the outcome. Repeat the process 50 times. Find and list the experimental probability of rolling a 4 after 10, 20, 30, 40, and 50 trials. So this now, all of these columns would represent my 5 different sets of 10. So my first outcome set would be a 6, 5, 5, 1, 2, 1, 2, 5, 2, 5. That would be my first set. And the 4 didn't come up at all. Okay, so I'm just going to kind of move this to the side a little bit. And for our note's sake, I'm going to write down these sets, and then I'll come up with those different experimental probabilities. So my first set is 6, 5, 5, 1, 2, 1, 2, 5, 2, 5. Okay, so that's my first set of outcomes when the dice is rolled. And for that probability of rolling a 4, that's 0 out of 10. My second set was 6, 2, 4, 4, 5, 1, 3, 3, 2, 1. All right, well, that one, we had some hits on the 4s, so that was 2 out of 10, or if we wanted to group things together, we're looking at 2 out of 20. My third set would have been 1, 1, 4, 3, 3, 2, 6, 6, 2, 5. And we've got just 1 4 there. So that would have been 1 out of 10, or generating 3 out of 30. My fourth set, oh, in the fourth set there were no 4s again. Okay, so then that would have generated 3 out of 40. And my last set of outcomes, this we only have the 1 hit, so then that becomes 4 out of 40. No, 4 out of 50. Oops. I'm gonna just look like that. Okay. So I have my separate experimental probabilities for the different sets of 10. If I take it out of the experimental probability of, I just want to make this smaller now. No. So my experimental probability of rolling a 4 out of 50 trials is 4 to 50. Now, if we want to think about it theoretically, to roll a 4, there's only one face that has a 4 on it out of the 6 total faces. So theoretically, the probability is about 17%. Now, when we first started out, we had 0%. The 2 out of 20 was 10% likelihood. The 3 out of 30 was also 10%. Then we got to 3 out of 40, which was 8%. And then finally, we landed at 4 out of 50, which is 8%. Ooh, we're very low here, so it's unlikely. But if we kept going with these sets, we might end up something closer to 17%. Last time I did this in my regular class, day school, and I ended up with 8 out of 50, which would have been 16%. Wow. So when we did it really in class, we did hit it right on the nail. So it did come up to be something close to the theoretical. This one with my Excel simulation, I ended up further away from it. But that happens with probability because everything's possible. So down here, it just says a couple of different bullets here about simulations, which is what we just did with Excel. An experiment can be simulated using random numbers. The random numbers can be generated using a calculator, tables, or computer spreadsheet. When designing a simulation, it is important to ensure that the experiment has the correct sample space and is fair. When implementing an experiment, be sure to organize your results in a frequency table that lists all possible outcomes and the number of times each occurred. Okay, so that's the end of lesson 3, experimental probability. There's no homework for this lesson.